All right, so as I hinted before, moving on to section 4 of chapter 5, we're going to be dealing with information about samples. And remember, what's the difference between a sample and a population? A population is an entire, it's everything, it's all women, or it's all NFL players, or it's an entire population, it's everybody. A sample is just going to be a subgroup of that. um, so we're going to pretty much do everything the exact same thing. There's just going to be some minor adjustments in the formulas. But the first thing you need to know is that just because they give us the mean and the sample standard deviation, it does not necessarily mean we will be able to use that information to make predictions about our population. So there's a couple of conditions. In the central limit theorem, you don't really have to worry that that's the name, but here are the two conditions. First of all, you have to pay attention to the size of your sample. If your sample is greater than 30 or greater than 30, then you can continue to use the information about the sample in order to make a prediction about the population. It says if it's drawn from any population with the mean and a standard deviation, then the sampling distribution approximates a normal distribution. So that means that as long as we have more than 30 in our sample, we can expect our distribution to be normal. It'll fall under the curve. Now, if it doesn't have a sample size, if there's not at least 30 pieces of data in the sample, then the only way you can use a sample size smaller than 30 is that you have to know that the population that it's drawn from is normally distributed. Okay, so let me give you some examples over here. So here's a population. Okay, now they're giving us information about our population. This population is not normal. It's got some peaks and then it comes back down, so it's not the normal thing. So in order to be able to use a sample from this population, the sample size must be bigger than 30. As long as we pick a sample size bigger than 30, then we can expect it to behave under normal, as a normal distribution. If we know that the population is normal, like this picture right here, this is a very normal population, then it doesn't matter what your sample size is. You can have a sample size of 30, you can have a sample size of 2. Your sample size will behave normally. So if your sample comes from a normal distribution, it's going to behave normal regardless of its size. If your sample comes from a population that's not normal, then it must be greater than 30 in order for us to be able to use it. So that's what the central limit theorem says. Also remember, and they're not probably going to use these symbols, but as long as we know that we're dealing with either one of these situations, then you can expect that the mean of the sample to be the exact same thing as the mean of the population. That's what this is saying. So in either one of these cases, the mean of the sample will equal the mean of the population. So notice down here, they're saying the mean of the sample right here is equal to the mean of the population. So the sample mean and the population mean are exactly the same. Same thing with this one right here. If it's a normal sample from a normal distribution, then the means are going to be the same. The standard deviation, though, is not. The standard deviation, you'll have to calculate the standard deviation for the sample using this formula right here. And I just crossed that because the symbol that they used out, I don't know why they're using the thing with the subscript. That is so confusing. I don't know why they did that, because they've already told us that we're going to be using S and X bar for mean and S for standard deviation. So we're going to have to calculate. And don't worry, I'll work this out in the examples that I'm going to do. But the main thing that you need to know is that the mean of the sample is equal to the mean of the population. The means are equal, but the standard deviations are going to have to be calculated. And the standard deviation will have to be calculated. They're going to give you this standard deviation, and then you're going to have to calculate the standard deviation of the sample in order to do it. All right, I'm going to go ahead and pause right here because I've done a lot of talking. I don't think it would be good to go ahead and start working a problem. Well, I guess I can. I can go ahead and work this problem. So here's using the central limit theorem, the thing that I want to make sure you understand. So here is a population. It's not normal. It's skewed to the right over here, and then we've got, this irregular hump right here. So this is not necessarily a normal population, but it says right here that our sample of 100 sleep times, so our sample size is over 30. So since our sample size is over 30, then we know that our sample will be a normal distribution. Okay? Okay, so what we have right here, it says the study found that the mean sleep time was 6.8. So we can find 6.8 to be right here-ish. That's the mean of the population. It's 6.8. I may have it over a little bit too far. And then with a standard deviation of 1.4 hours. So you go 6.8 and you go over 1.4 hours, and that'll be one standard deviation away. Over another 1.4 hours, that'll be another standard deviation away. And that's how that, maybe I can draw it real quick. It's, I'm going to just try to get this on this curve that you're used to seeing. They said it is 1.4 hours. So 8.2, and then 1.4 hours is going to be 9.6, and then one more 1.4 hours is going to be 11 hours, and then go back this way, take away 1.4, so that will be 7.4. One standard deviation away, take away 1.4, that'll be 6, and then take away one more, and that'll be 4.6, I believe. All right, so that's what 3 standard deviations on either side of 6.8 looks like. Now, this information that they gave right here was for the population. It says now that you understand that this right here is population information, the mean is 6.8, and the standard deviation is 1.4. Now we're going to take, and this was, they didn't tell me how big the study was, but this is all college students. Okay, that's what the sample size is right here. Then we're going to go down here to just a sample size of 100 students. Just a sample size of 100 students. And they told us in that central limit theorem that even for the sample, the mean's going to be the same. The mean of the population is going to equal the mean of the sample. This is for the population. This is for the sample. Okay. But what's going to be different is the standard deviation. Because we have a smaller sample size, we have to calculate the standard deviation for the sample. And if you remember what it was the standard deviation for the population divided by the square root of the sample size. So the standard, the standard deviation for this sample down here is not going to be 1.4. We're going to take the 1.4 and we're going to calculate it and divide it by the square root of 100. So 1.4 divided by the square root of 100 is going to be 0.14. So that means that for the sample, the standard deviation is not going to be the 1.4 that it was up here. Instead, it's going to be 0.14. So on this side, we're going to say 6.8 plus 0.14. So that's going to be, hold on, I've got it written down right here. That's going to be 6.94. And this one would be 7.08. And this would be 7.22. One standard deviation for the sample is going to be away. On the left-hand side is going to be 6.66, 6.52, and this one is going to be 6.38. Now, I want to make sure that you understand that I'm not explaining why we do this. I'm not explaining that at all because I don't know. This is above my pay grade. This is something that other statisticians have calculated to be, true. It has to do with the difference between the population and the sample. I don't have an explanation for you. That's, like I said, sometimes I just don't ask why. I just go, okay, if you say so. And this is exactly one of the situations. I'm not trying to understand why we adjust the standard deviation for the sample. I just know that that's what that central limit theorem right here told me to do. That's what this thing right here told me to do. The sampling distribution of means has a variance equal to that, and the variance of the population is divided by the square root of n. So they're just telling me to do it. We're not going to do much with this right here. I don't think I'm ever going to ask you to calculate that. But I am going to expect you to be able to find the standard deviation of the sample by using this formula. So that's that one. This one right here is the same thing. The difference here is this is a sample size is 4. So that's not bigger. That's not big enough. But it is okay because this is the distribution of the population, and it's a nice normal curve for the population. So since the population is normal, even this small sample size of 4, it's going to be normal as well. So I challenge you to see if you can't do the same thing that I just did. Redraw your, calculate your new sample size, and then draw the distribution for the sample and demonstrate 3 standard deviations using the sample standard deviation. And I will start my next video with my answer to this question.